Welcome to this session. In this session, we are going to give the second example on numerical differentiation. So the question is, the table below shows values of a certain function. So we have x and then the value of the function at x. When x is 1, value is 2.7183. 1.2, 3.9841, and 1.4, 5.6773, 1.6, 7.9249, 1.8 is 10.889, and 2.0, 14.778, 2.2, 19.855, 2.4, 26.456, and 2.6. The value of the function is 35.006. So those the table given. So the first bit of the problem is to draw a difference table. So draw a difference table. Draw a difference table up to fifth difference and use the difference table to approximate the value of the second derivative of the function at 1.0. But these are the f values. So the values of the second derivative at 1. So this is how we'll draw the table. So we'll have column for x, 1 up to 2.6, and then value of the function as given in the table, we have this. And so we'll have the first column, the first difference, second column, second difference, third column, the third difference, fourth column, the fourth difference, and fifth column, the fifth difference. And when you are writing these values, ensure that you leave spaces, one line for consecutive values where the differences will be written. And to get the differences, just for example, this one here, you simply take lower number minus upper number. So 3.9841 minus 2.7183 is what gives us 1.2658. And so this is a trend that you take to get all the differences, lower number minus upper number. And because the reference point of x is 1, so you'll have identify where 1 is in the difference table. So draw this line 1, that value and its corresponding f value, and then have this diagonal. So this diagonal drawn in pink are the values that we are going to use. So in the first column is where we'll have our first forward difference. And we are using forward difference because 1 is at the beginning of the difference table. If it was a value below the difference table, then we'll use Newton backward differences. But this we're using Newton forward because is a value we want to find the derivative for value which is at the beginning of the difference table. So that explains why these are forward differences. So this is the first forward of F naught, second forward of F naught, third forward of F naught, fourth forward of F naught, and fifth forward of F naught. So therefore now let's go and approximate the value. So solution, we know that, let's break that problem into two parts, into some subparts. So approximate f double prime at 1.0 using, so Roman 1, 2 terms, Roman 2, 3 terms, Roman 3, 4 terms. So let's say this is the first question. We have the table, we have drawn the difference table, and then they tell us to approximate the value of the second derivative at 1.0. Now, we know that the formula is the second derivative at a point x naught is given by 1 over h squared into second forward of f naught minus third forward f naught plus 11 over 12 fourth forward of f naught, and then minus 5 over 6 fifth forward of f naught. So this is general formula. We are using Newton forward because the value x equals to 1 is at the beginning of the difference table. So first two terms means we'll have f double prime at 1.0 will be approximated by 1 over. Now in that table, the difference between consecutive x values is 0.2. So we'll have 0.2 squared into, now this is the second forward, that's what is in the question. So second forward, let's go to the table and see how to read that value. This is our difference table. So this is the column where we have the second difference. So you don't pick 1.2658 at the first difference, because this is the first difference. So this is the value that you pick, 0.42740. So I'll have 0.42740 minus third is 0.12700. So these are the only two terms. So we stop at this point. When you work out this one, you'll get 7.51. Roman 2, 3 terms. So f double prime at 1.0 will be approximated by 1 over 0.2 squared into 0.42740 minus 0.12700 plus now 11 over 12 into that difference is 0.035100. And when you evaluate this, your answer should be 8.314375. Roman 3, using 4 terms. So the derivative at 1 will be approximately 1 over 0.2 squared into 0.42740 minus 0.12700 plus 11 over 12, 0.035100 minus 5 over 6 into 0.011200. When you work out that one, your answer will be approximately 8.08.081041667. That is part 1. Part B, assuming, not assuming, given that the function f of x is given by x e raised to power x, find the approximate, the absolute errors and percentage error in each of parts 1 to 3 of A above. So what we do, because we are calculating second derivative, so let's get the second derivative of this function. So the first thing, f prime of x, use product rule. So this to be u, this to be v. So u prime is 1 times v is e raised power x plus v prime is e raised power x times u is x e raised power x. So which can be written as 1 plus x e raised power x. Now the second derivative will be, we differentiate this one also by product rule. So this to be u, this to be v. U prime is 1 times v is e raised power x. V prime is e raised power x times this bracket to be 1 plus x e raised power x. On simplification will be 1 plus 1 plus x e raised power x, which is 2 plus x e raised power x. So this is the second derivative. So therefore, the exact value of the second derivative at 1.0 will be given by 2 plus 1.0 e raised power 1.0. 2 plus 1 is 3 e raised power 1. So this is the exact derivative. So we know that absolute error is given by difference between exact value minus approximate value. So which means that for part 1, when we have two terms, then let me call absolute error E1 will be given by the exact value is 3 e raised power 1 minus the approximate in the first case using two terms was 7.51. So absolute value in this difference will give us 0.64448454. And then which means that percentage error in this calculation would be error 0.6448454854. You divide by exact value is 3 e raised power 1 times 100%. And when you work out this, you should get 7.9075132227%. So that's the error and percentage error in the first case when we are using only two terms. Roman 2, if you're using three terms, then let's call the absolute error E2. Exact is 3 e raised power 1 minus approximate. In this case, our answer was 8.314,375. When you get this difference, its absolute value will be 0.1595295.146. So which means that percentage error in this case will be 0.1595295.146 divided by 3 e raised power 1, which is the exact value, times 100%. This will give us 1.9562542.9%. And you see, if you compare the previous case, when we used 2 terms, error was 0.6. Here, error is 3 terms is 0.1. So the error has reduced. Similarly, the percentage error for 2 terms was 7.9%. You see here we have 1.9%. So even the percentage error has also reduced when we increase the number of terms. Let's see for the case of 4 terms. So let's call error E3 will be the difference between 3 e raised to power 1 minus the approximation. In that case, we got our answer to be 8.081041667. So this error will be 0.08380381838. You see, the value of error for 4 terms has also become less than what we got in the case of 3. This was 0.15. So percentage error in this case will be 0.08380381838 divided by the exact, which is 3 e raised to power 1 times 100%. When you carry out this computation, your answer will be 1.027656729%. You see also the percentage has reduced. The previous one was 1.9, here is 1.0. So from these 3 results, we clearly see that the more terms we use, the less the error, and the better the approximation. So to get a better accuracy, then we must use more terms in the computation. So that's what we have. Thank you.